All right, 7-7 inverse relations and functions. So starting off, what is an inverse relation? An inverse relation is, we'll start off by saying, like, if we have a relation, right? Think of any kind of like linear function or something like that. That's a relation. If we have a relation that pairs, we'll say an A, or actually no, let's say an X that's in your domain, right? And this means is in, you could say is in, or is contained. So an X in your domain. So if we have a relation that pairs an X in your domain with a, where do I want to go? Y in range, then the inverse relation pairs Y with X. So your normal relation, if we'll say your relation has X, Y, then the inverse relation would be Y, X, right? You normally think about like independent and dependent variables. The independent and the dependent variables would swap spots. So that's what an inverse relation is, and then we'll generalize it to, or not generalize it, we'll make it more specific to inverse functions later on. One thing that will be useful later on whenever we start talking about functions is the vertical line test, right? Hopefully that's review for you, but it's, I don't know how to word it. I know how to say it. If you have a graph, we'll say if you have a graph, a graph of a relation, then it is a function if a vertical line only touches it once. If any vertical line only touches the graph once. Right? Think about a parabola, just for example. Some kind of random parabola there. The vertical line test says that no matter where we draw our vertical line, it has to only touch it one time, right? So the parabola passes the vertical line test, which means that it is a function, or the quadratic is a function, right? So I think about the vertical line test a lot whenever I'm thinking about, is this a function, is this not a function? All right, example number one, we're going back to the relations idea. So example number one, let me do this in a certain color. I'll do black. Example one, we'll say find the inverse relation. Find or list the inverse relation. So remember back whenever we were given t-charts of it like this, of our points. So we have that is our relation. And we're told to find the inverse relation. Well, the inverse relation, all we do is we swap our values. We swap our x, y's. So our inverse relation would be x, y, and 2, 1, 3, 2, 4, 3, 5, 4. Right? I just swapped the spot. So this is the relation. This is the inverse. Alrighty. So that's inverse relations. You take your x and your y and you swap them. So example number, what example is this? Is this going to be number 2? It is going to be number 2. All right. Example number 2. We have y equals the square root of x plus 2. And we're supposed to, again, with the same directions, find or list the inverse relation. So this is our relation. What we want to do is we want to list it with the variables swapped, right? That's what we did up here. We just kind of swapped the variables. With the points listed like that, it makes it just a little bit easier. But here we're going to have to do a little bit more work. So what I like to do with these is right at the beginning, I swap the variables within the equation. Here's what I mean. I'd write x equals root y plus 2. Now I'm going to solve for y to get my inverse relation or my inverse function. So I'll square both sides. So this will be x squared equals y plus 2. And that will give me y equals x squared minus 2. So this is my inverse relation. Now let's think about this. Are these two functions? Right, are they functions? Well, y equals root x plus 2. That does a graph something along the lines of that. Oh, here, let me change colors there. Something along the lines of that. It's like a sideways parabola. So this is a function. And then the other one is a parabola, and we can probably graph that in our head and say, well, yeah, this has to be a function. Right. It won't always be the case that they're both functions. A lot of the time, one of them will be a function and the other one will not be a function. So let's look at that more and look at number 3. Number 3, we're supposed to graph the function and its inverse. And then we're also supposed to determine if they are functions. All right. So our original is y equals x squared plus 3. Well, just because, let's list the domain of this. That way we can remember what domain is. So domain, what can we plug in to that? Well, we can plug anything in. So the domain, we're going to say just all reals. Right? That's the fancy symbol for all reals. It's the the paragraph symbol turned into an R. Now, let's think about the range. The range is actually kind of special, though. What is the smallest y value that we could get? Well, the smallest would be if this was 0. That can never be negative, right? The x squared can never be negative. So the smallest one is going to be 3. So we're going to say this is all reals given, that's that line, that y is greater than or equal to 3, right? So y has to be bigger than 3. That's the fancy way of saying that. All right. Let's find our inverse and then we'll graph them together and we'll graph them on the same thing. So just like in the last one, we're going to swap the variables and then we're going to solve. So we'll say this is x equals y squared plus 3. So now we solve for y and get y by itself. So this will be x minus 3 is y squared. And then we have to put a square root in there. And we created the root, right? In the last one, the root was already listed. We created the root this time, so we need a plus or minus. And I'm just going to write it the other way around because it makes it look nicer. So just like that. So this is the relation. This is the inverse. All right. Let's look at the domain and range of this guy. The domain of the bottom one, what can we plug in there? What can we plug in for x? Here we have to think more about it, I think, at least, because we've got that root. We can't have a negative under our root, right? So the smallest thing that x can be would be 3, right? Because that would make the root 0. And root 0 is okay, but root negative anything is not okay. So we're going to say that it's all reals, or here, I'll go back to my blue. It's all reals given that x is greater than or equal to 3. Now for our range, well, we could get anything out of our range, right? Our y could end up being anything. So we're just going to say all reals. We should notice here that this and this are the same. This and this are the same. That would be a good thing to know. The domain and range of the relation and the inverse relation, you swap the domain and range spots, right? It's the same rule, but you have to swap the domain and range. Now let's look at graphing this. So we're going to go something like this, something like this. Oh, and something that will help us to graph this is to know that a relation and its inverse. How do I word that? Are reflections over y equals x. You've probably done You've probably done reflections over y equals x before, and this we're going to end up using that idea, right? Because the parabola there, the original relation, is really easy to graph. The root function, at least I think, is harder for me to think about how to graph it. So here, I probably need to extend this just a little bit more. We'll extend it to there. So our relation, I'll graph it in green. We're going to have y equals x squared plus 3. So my vertex is at positive 3, and my parabola is facing up. And I'm just going to go that far with it. Now, if we were to graph our y equals x, that'd be that. This is y equals x. Reflecting it over the line y equals x, we would end up getting, let me graph this one in orange, a parabola on its side like that. Right. This would be a root function. Now, are they functions? The original relation is a function, but the orange one, it fails the vertical line test, so it is not a function. Right? We're still able to graph things that are not functions. That's something important here. That might be the first time that we're doing that, where we're graphing non-functions. All right, that's that example. Let's move on. Now we have the whole idea of inverse functions, and we have some fancy things we can do with that. Inverse functions. And kind of like how I talked about conjugates, you think about inverse functions as a pair, right? Um, so we say if f and f inverse, that's what that means, are functions, then they are called inverse functions. Right? So if f and f inverse are functions, then they are called inverse functions, right? So here we're saying that they have to both be functions, right? And then we say explicitly the domain of f is the range of f inverse, right? We kind of already said that, but I didn't write that down. And then we also say the range of f is the domain of f inverse. All right, example number 4. This says find f inverse and find the domain and range of f and f inverse. So our problem here is, or our problem, f of x equals root 2x plus 2. What's our domain? Our domain is our x. We can't have a negative under our root, so we think about what would make the root 0, right? What would make that 0? Well, if x was -1, right, think about this. 2 times -1 plus 2, that'd be -2 plus 2, which is 0. So we're going to say that x will be all reals given that x is bigger than or equal to -1. Our range now, that's our y, or our f of x. That's over here on the other side of the equal sign. So the root tells us that we can only get positive things out of it. So the range is going to be all reals, given that we'll say y is greater than or equal to 0, right? It has to be positive. That's the way they're saying that. It has to be positive or 0. Now for our inverse, well, we swap our variables. So this is going to be x equals root 2y plus 2. So we square it and we get x squared is 2y plus 2. So x squared minus 2 is 2y. And y is 1/2 x squared minus 1. So we should start seeing a pattern here. The quadratic and the root function are inverses of each other. Right? A lot of the time we only talk about the principal root, the positive root of our root function. That way it stays to be a function, it's not just a relation. So here, our domain and range of this guy well, let's think about this. Our top function is going to be something along the lines of this. Actually, I think it's going to be something along the lines of that, a little bit to the left of the axis. So if we were to reflect that over the line like that, we end up getting something like this. the other side of our parabola isn't listed, right? It's only the positive side. So only our positive x's. So we're going to say that it's going to be all reals, given that x is bigger than or equal to 0. And it also ends up lining up with our range of the other one. Then we can see that the range of this one, well, the smallest thing that y can be will be -1. All right. So really, we didn't have to find the inverse there. We could have just gone off of the domain and range of our function. All right. Next up, we have composition of inverse functions. Composition of f and f inverse. F of f inverse of x is x. The fancy way of writing this would be f composed of f inverse of x is x. And we can also write the reverse of this. F inverse of f of x is x. So we could write that as f inverse composed of f of x is x. Right? And think about that. You start off with your x in the middle, then you do f inverse to it and you get y, right? And then you do f of it again and you end up getting x back, right? They reverse each other, and if you do two reversals, then you're back to where you were. So there will be some problems on the homework like this, like example number 5. What are we saying? We're saying our function is f of x is x minus 7 over 6. Find f inverse of f of x. Oops, I need parentheses here. Oh, not of x. We're plugging in a thing, a number. Plugging in the number, we'll say 374. And then we'll say, and find f composed of f inverse of, I don't know, some huge weird number, negative 99 pi. Well, based off of what we have up here, this does not matter. Our function that's listed there, we don't care about it at all, right? We just care about this statement there. So we could say, well, f inverse of f of 374, well, that just has to be 374. And the other idea of it is, well, f composed of f inverse of negative 99 pi has to be just plain old 99, negative 99 pi, right? We don't care at all about our function because we have that rule. All right, that's our lesson. I know this one went a little bit long. Make sure you have these written down, and I will go over this in class with you also. All right, bye-bye.